Well then, hello everyone. Yeah, I'll be talking about my KeySteal vulnerability that I found a few months ago, and well, let's get started. First about me. Yeah, I'm Linus, and I'm an independent security researcher from Germany. My main focus is iOS and macOS, and I'm also currently studying CS at the University of Koblenz. And you can find my website on the slide. And yeah, my explorers will be found on my website and also on GitHub. So what am I going to do? What am I going to talk about today? First of all, just shortly, what is the keychain? And yeah, basically, how can you access it? And afterwards, I will be talking about the internals. That means yeah, I'll show you how everything works behind the scenes. And yeah, then my exploit, and how I will fix it, and then a small demonstration. Let's talk about the keychain. Well, first of all, what is the keychain? Yeah, the keychain is the central place to put all your passwords, certificates, yeah, keys, whatever you want. And basically, there are two keychains that are important. There's a login keychain. Each user has a login keychain. Yeah, personal keychain, where you put all your personal passwords. And there's also a system keychain, which is used the system. And additionally, you might know that there's also an backup keychain. I will not focus on this in this talk because it works completely differently. The login keychain. Well, I've put a photo of keychain access there, just so you know what it looks like. And yeah, as I said, you put all your personal passwords, your personal keys, everything you want to be encrypted without other users being able to access them, put them on the login keychain. And it's encrypted using your login password. So that means when you log in, yeah, it will automatically be decrypted, and yeah, then applications can access the login keychain. And yeah, what uses the keychain? Basically, there are quite a lot of Apple services like iCloud. You use the login keychain, and also yeah, quite a few apps like Slack, Twitter, and yeah, many more use the login keychain to save your passwords when you're using the safe password functionality. System keychain. The system keychain is yeah also important because it stores mainly your Wi-Fi passwords, and yeah, it's more interesting when you're yeah, when you're a large company who wishes to yeah, basically deploy apps or make sure that yeah, it's integrated in their network, and it's also encrypted. But of course, it cannot be encrypted using a user password, because in that case you would need to encrypt the encryption key with the user password, and you just can't do that because of this. It's stored in the file system. Key is only readable by root, and yeah, you can, as a normal user, you can check what's inside system keychain, but you won't be able to see the actual passwords. All right. Some advantages and disadvantages about a keychain. Well, the keychain usually is a simple and safe way to store all the passwords, unless you become an expert. And yeah, you can also use it to share credentials with other apps. Problems about it is, of course, it's a single point of failure. If you lose your login password and have everything safe in a login keychain, then yeah, you just won't be able to get your passwords again. And second disadvantage is that the attack surface of the keychain is very large, because Apple decided to create one process that handles the keychain and thousands of other things. And basically, if you own this process, yeah, the contents from the keychain. Accessing the keychain. I just show a quick example of that. But before I do that, first of all, I'm talking about keychain items. What is that? Basically, everything inside your keychain is a keychain item, and there are multiple classes of items: internet passwords, keys, certificates, stuff like that. And yeah, each item has attributes, and these attributes can be usernames or URL or whatever you want. And also, if you use the keychain and know about secure nodes, then I have to tell you that secure nodes are not a class, but they are just a generic password. And yeah, the keychain access program just sets one of the attributes to secure node, so it knows it's not a normal password but a secure node. Well, small example how you can access the keychain. Basically, you should focus on this. It's actually pretty easy. You just have to create a dictionary with your query, and you have to put in there the class. So the system knows which class you're looking for items, and the limit. Usually, you can just put no limit in there. Just say, okay, I want everything. And you don't have to tell the system if you want to get the attributes of the items or if you want to get the actual data, which is encrypted. And if you get the actual data, then there might be a prompt for the user to allow that. Yeah, additionally, you can just put other attributes in there, which to search for. And you pass this dictionary to a function called matching, and yeah, it returns you an array of dictionaries. Each dictionary is just the keychain item. That's basically this part down there. Right, then let's go to keychain internals. How the keychain works behind the scenes. Basically, there's one process called security, and it's responsible for the keychain, and it has the encryption keys, and it's doing the access control. I'll tell you a bit more about access control later. And yeah, then we've got a security framework, which is implementing those high-level APIs. Yeah, I'll just say, I don't mention API, for example, it's implemented by the security framework. And yeah, there's also a low-level API, and there's MIG, the market interface generator, and basically you can use MIG for remote procedure calling, and yeah, those high-level APIs then use low-level APIs to actually communicate with the security team. An interesting part is how does this communication work? And this communication works through MAC ports. And yeah, MAC ports, for those of you who don't know, they're just message queues implemented in Chrome, and they work like a mailbox. That means you've got one process that basically owns the port and is able to read messages from this port, and they have many processes that are allowed to send to this port, and yeah, each of these processes holds its handwrite. And each port also has a name, and this name is basically just an integer, and it's not unique on the system, so it's unlike a normal TCP/IP port. And yeah, these names are just unique for each process. That means if I've got two processes, A and B, then process A may have port 1, 2, 3, 4, 5, and process B may have port 1, 2, 3, 7, and they could still reference to the same port internally. And what's also important about these ports is when I create a new port, then other processes won't know about it. So I first have to tell other processes about my port. There's also a special kind of MAC ports, MAC task ports. And yeah, each process has one of these MAC task pods, and allows you to modify the process, like reading, writing, creating new pages, setting permissions, whatever you want. And you can also use it to identify a process. We'll need that later, because security B will use it to identify other processes. And yeah, once your process dies because you exited for whatever reason, then this MAC task pod will also be deleted. MAC messages. Of course, you need to send messages to these pods. And these messages are just some structured data. You've got a header and a body, and the header contains basic information like the port you wish to send the message to, and you can also put a reply port in there to basically tell the recipient where to send a reply to. And of course, you need to put a price in there. You can also put a message ID in there, so the recipient knows what kind of message this is. And then there's also a body, and this is, basically the body has two parts. One part is passed by a comma. We can disable this part, put in some flags in the header. And this kernel process part may contain other MAC parts you wish to send to other processes, or it can also contain some memory, file descriptors, quite a few things, and the rest of the body is just whatever you want. And you can just use a function called message to send this message to a port, and then it will be queued in the kernel. Of course, unless there's when the queue is already full, the port's queue is full, then the message cannot be queued. So you need to wait until you get. As a quick example, if you would be Twitter and you would like to, if you're Twitter and you would like to find out my password because I used a second password function, then you would need to send a message like this. And what you put in this message is your query. Of course, in this case, you just put in there, I want an internet password for Twitter and username, my username. And you also put a reply port in there to get a result back. Send it to security D, and after some while it will take out the message, process it, and then basically send the result back, which is my super secure password. And what you need to know is if you look at both messages, you will see that the reply port is different. The reason for this is very simple, because, as I've said, port names, the numbers are unique per process. So usually, like in this case for Twitter, it has a number 1337, and it sends the message, and the kernel will give a security D the same port, but with the name 4142, for example. Well, now there's just one question. I told you that when you create a port that other processes don't know about. And it also means we can't just send a message to the security D service because we don't know its port. And we first need to find out its port, and how do we do this? Through launchd. What is launchd? You may probably know that this is the init process on macOS. And this launchd process basically has a bootstrap port that it sets, and whenever a new process is, whenever you spawn a new process, then this new process will inherit your bootstrap port, which should usually be launchd's port. And you can then use this bootstrap port because every service needs to check in with launchd and sends a message to launchd through this bootstrap port, and then just basically sends its port, let us receiving messages on, and and the name, so other processes can just request the support through the name. And in the case of Twitter, for example, you first need to send an HTTP message that we are looking for a special server. In this case, our security server, which is the name of security. And of course, a reply port again. And we send this message, and we will get a reply that will contain the port of security and send back to us. And now we can use this port to do the communication. Now about keychain access control. Of course, there needs to be some access control because you don't want arbitrary processes to just get all the passwords. And because of this, there's an access control list associated with each keychain item. And basically, it's just a list of applications that are allowed to access the item without a password prompt. Of course, arbitrary processes cannot edit this ACL. Only the user is allowed to do so, or applications that are already in this list. Now the question is, how is it enforced? Mm-hmm. And it's actually pretty simple. Before you're allowed to do anything in security, before you're allowed to send any requests for a keychain, you first need to create a session. And when creating a session, you send your special task port, and security will then use this task port to get your proof signature and basically determine later if you're allowed to access an item. And what you do is, first of all, you would need to send a create session request, and you would need to put a task port in there, and also a reply port to get a result back. The reply port is also needed because later, when we are doing additional requests, we don't want to send a task port each time, and because of this, we only include our reply port in a message, and security D will then look through its list of sessions and will then find our reply port. There's also a way to register additional reply ports with security D, for example, when you're doing multi-threading. And what you do is you send this message, and security D will then create a session and send OK back, and afterwards you can just do the access. Okay, that was the wrong part. Now it's time to actually exploit the keychain. And first of all, I just want to tell you how I found the bug. And I needed a sandbox escape because last year I created a WebKit exploit, some of you may know. And I just thought that having a sandbox escape would be very cool. And I looked into the sandbox profile of web content, which is the process that runs the JavaScript. And it's allowed to access COM Apple security server, so the service. And just because of the name, because it contains security, I just thought I have to look into that. And didn't find a sandbox escape, but without a bug, I wouldn't be here. And what I did was I looked through the documentation, and I found this article about hosting guest code. And I never heard of this feature, and I guess none of you heard about it either. And basically, this feature is implemented in security D and allows you to tell the system that you are now launching a plugin, and whenever you are now doing keychain requests, you tell the system, okay, it's not me doing the requests, but the plugin I loaded. Problem is this API is completely broken. It still doesn't work. So Apple refused to fix it. And also has a vulnerability. It's the only thing they fixed. And vulnerability is basically in this function. It's called hosting port. What does this function do? Basically, you've got two modes to enable this guest code hosting feature. That's a proxy mode, which is the easier mode. You just tell the system, okay, I'm launching a plugin, and tell where the plugin is on the file system, and the system will do everything for you. And there's also this dynamic mode that can be enabled using this function. And yeah, you need to pass a MAC port to which will then be used by security, and basically when you process then does keychain requests or needs its code signature validated or things like that, then security D will send a message to the port you registered, and you don't have to send a reply back. What's the problem about this function? Well, it looks like this, and yeah, this is not. There's no bug in there. It's just checking if you're already in dynamic or proxy mode, and refuses to set a port if you're in one of these modes. But if you're currently in no mode, then it will just register the port in your sessions. Looks correct. Is correct. The bug is here. There's a reset function, and this will be invoked when your session is destroyed. And your session usually will be destroyed when your process exits. And what it basically does is it checks in which mode you are. And if you're in dynamic mode, then it calls destroy on the port you passed. What's the problem with that? It's calling mark port destroy on the port you passed. And what this means is you can just send a random port to security D, and when you send a port it already knows about, then it will not get an additional port, but it just will get a new reference on that port. Problem is that when you use mark port destroy, then the reference count will be set to 0. And what they should have done is they should have used mark port deallocate, which will just drop the additional reference it got. And when all these references get destroyed, then you basically have a use of the free in there, not with memory, but with mark ports. And you just have some parts of security D will then think this port still exists, and we'll try to use it, but of course it just won't work. And you can also then replace this port. So what's the attack plan? Yeah, of course we can now free an arbitrary port on security D, but what can we do with that? We just need to go back to the security sessions, and I told you that to create a session you have to send a task port. And when you send your task port, this session will be tied to this task port. And what you can do now is you can run a process which just creates a session and then use a bug to free the task port. And now you've got a session that just has a dangling task port, and you can not access it anymore. And it doesn't sound too useful, but it actually is. And before I tell you what can be used for, just this small part here, we're just interested in this part. This is the method that is called when you're creating a new session. And the interesting part is this one. What it does is it checks if the task port you sent is already tied to a session. And if that's the case and you're asked to create a new session, it will think you've got amnesia and will reset your session. And when resetting your session, this method will be called, and this part is interesting because this client identification setup function just reloads the code signature from a process, but it's using the process ID that it has saved. and the process ID is saved the first time you created the session. So it is not taking the process ID of the process that actually made the request to reinitialize the session, but it's taking a saved process ID. And yeah, what can we use this for? Basically, if we can create passport of the session and then somehow reinitialize it and make sure that the process ID number of our process that originally created the session is now the ID of another process that has a special entitlement called com upload private security allow migration, then we'll be able to access the keychain without any password prompt, because there's this function that checks the SL and it has this if, and it checks if your process is signed by Apple, and it has this special creator entitlement, and basically when it's the case, it becomes true. And also this comment is from Apple, it's not from me. They already tell you if you pass this check, then you automatically win, and there will be no prompt. Just need to find a process that has this entitlement. We can use the entitlements database, and we get a list of processes that has these entitlements, and we just choose one of them, like the internet content creator. And if we do all these things, then we'll be able to access the keychain without a password prompt. Now there's just one last problem. The problem is that when we freeze the session, we don't have access to it anymore. And what we need to do is we somehow need to replace this task port of the session. And we can do that by sending a huge number of ports. And eventually one of them will get the same number as our task port had, because Kernel just has a list of used ports and it just likes to reuse port names. All right, got a huge attack plan now, and I will walk you step for step through it. And we'll start with this, with security D and our KeySteal process. And the first thing we need is a helper process. Okay. Now we need this helper process to create a session with security D first. And to do that, it needs its task port. You can just ask the kernel for its task port. And it needs to create a new connection port that will be used for security D to send replies. And what we do is we just send a message with our task port and our connection port. And I would not put the port numbers there because they are not really interesting. And what security D now does is it creates the session, the sessions, and it puts your task port in there and creates a new session where this connection port will be put in. And afterwards, we'll get a reply. Okay, it worked. What we now want to do is free this task port. And to do this, we need, again, a new process, which also has a task port and just creates a connection port. And what we do now is we send the task port of the helper process to our trigger process. That's what you can see here. We just send this task port from the helper to a trigger process, and now the trigger process has the task port. And now we can do the actual free. And how do we do that? We need to create a session first. Okay. Just creates a session, puts the task port in there. And we get a reply, worked. What we need to do now is we use our hosting port register function, and we send a message with a hosting port, and this will be the task port of our helper process. And what happens is this task port will be put in the session as hosting port, and we'll get a reply back that it worked. And now we can just let the trigger process exit. So it exits, and its task port and its connection port will die now. And the kernel will send security D a message that basically says, okay, this task port in there just died, and yeah, the port doesn't exist anymore. And what the security D will do is, okay, it will just delete your session. And what happens is it will call my port to deallocate on the task port of the trigger process and on the connection port. So this port will be gone now. And what it does now is it calls mark port destroy on the hosting port. And because the hosting port is the same as the task port of the first session, it will also die now because yeah, it's removing all references, setting the reference count of this task port to 0, so it will be gone now. After the process died, it will look like this, and our task port just doesn't exist anymore. There's now a session that is tied to a non-existing task port, and this session will never die because yeah, security D will never know that yeah, the associated task port died because there's no associated task port. So even if our helper would die now, then the kernel would also send a message to security D telling it that the process died, but the task port will just get a new number, and when it goes through the list, it just won't find a task port in the list of sessions. What we need to do now is we need to regain access to our session. And yeah, we do that by sending a huge number of ports to security D. But first of all, we should create a new session because yeah, currently we don't have one. Or at least security D doesn't know that we have one. We just send this message again, we create a new connection port, and yeah, it will be put in the list of sessions. And you can see there that even though the task port of the first session should be equal to the task port of the second session, that isn't the case because the kernel just assigned it a new number. We get a reply, it worked, and now we can yeah, just send new ports to security D. And to do that, we will need a task port and a third connection port. Yeah, need quite a lot of ports here. And what we do now is we send security D a message that we would like to add a connection to one of our sessions, in this case, the second session. And this new connection port will be put in the list. And yeah, will tell us it worked. And now we can just ask security D to create another connection, but this time we use our third connection port as a task port, and we use our task port to, yeah, just to test if things worked. In this case, we will get a reply that it doesn't know the task port because, yeah, if you look there, our connection port just isn't a task port. What we do is delete the third connection port, and when we do this a few thousand times, takes a few seconds only, then yeah, when we do this step of sending the third connection port to security D and registering it with our session, then the third connection port will get the same number as the task port had. So as you can see, this port and this one, they are not the same because the kernel assigned them the same number. And so yeah, we get a reply. And of course, we first need to find out if things worked, and we do this step again, and this time our task port will be registered with the first session because security D now thinks that our third connection port is about a task port. And we get a reply back that everything worked. And yeah, now we know that it's quite succeeded. Yeah, what we need to do now is we need to send this third connection port, the fake task port, to our main KeySteal process. Just like this. And what we need to do is we need to send a receive right. The reason is simple. Our helper process will soon die, and we need to make sure that our fake task port won't die as well. And yeah, you can do that by sending the receive right somewhere else. Now, what we need to do is our helper process now needs to access the internet account creator. And yeah, now I've just written the process ID numbers to the session and to the helper process. And right now, the process ID 1337 is the one of the KeySteal helper. But if we do an exec now, then first of all, there are quite a few ports that will die because the helper process basically dies in this process. And then the internet account creator will be there, and it will have exactly the same process ID because we used exec and not fork. And yeah, just additionally, I will rename this connection port to the fake task port now. And what we can do now is use our fake task port to reinitialize the session. And we just do that by asking security D to create a new session, and security D will see that the session already exists and will reinitialize it. And by reinitializing the session, it will use the saved process ID to get the entitlements and code signature and other things. And it will get the code signature and entitlements from the internet account creator because this is the one that has the process ID 1337. So now our connection is registered with the session, and security D thinks that the session is owned by the internet account creator. And we get a reply back that it worked, and now we basically won because we can use this session now to just ask security D to give us whatever passwords we want, and there won't be a password prompt because it thinks we are the internet account creator, which is allowed to access the keychain without a password prompt. So we won now. Before the short demo, I'll just show you how Apple fixed the bug. First of all, what Apple tells you. They tell you that they fixed the use of the free issue with improved memory management. I really like to see that improved memory management because I didn't talk about memory at all, so it's not a memory bug. But okay, if they think it's one, I don't care. And what they did is, or let's rather say what I think they did is, because you're not allowed to do something. So I didn't do that, but just asked an Oracle what they did. And it looks like they replaced the smart port destroy with deallocate, which is correct. So you won't be able to free the port. And it also looks like they changed this setup function. So when you now reinitialize the session, it will not only use the process ID that it saved, but it will also use a generation number. And the generation number is just a 32-bit number that is incremented each time you do a fork or an exec. And basically you would need to exec 4 billion times to be able to pull out this attack again if you find a bug like I did. So even if you could find a bug to free a port, then you just couldn't exploit this anymore. All right, now the demonstration. Why can't I track this too? Run this. Basically, this is showing you that I'm not an administrator and that I'm running macOS Mojave 10.43. And what I do now is create a new item, a keychain using keychain access, a demo item, and just put a random password in there. And see the password there. And now I'll run my KeySteal daemon because I decided to make this a daemon so other processors can just request the session, and it takes a few seconds, and then the exploit succeeds. And now we can use just stop it for a second. What you can do now is there's a program called security that you can use to dump the keychain, but usually it would cause a password prompt to appear. But I injected a small library in this security program, and now when it does any requests to the keychain, these requests will be modified to include our fake task pod. And what happens is that it will just run and will put out, basically show you all the information. And as you saw, there was no prompt, nothing. And I can just look through it and we will find a demo item in there. And we'll find the data there. And the data is the password. And if you just look in there again, for keychain access, there will be a keychain prompt, and you'll see both passwords are the same. And I can also show you that I can read the system keychain even though I'm not an administrator. Just open it up. I've got my demo Wi-Fi in there, and I'll just look through the dump security tool, and we've got demo Wi-Fi and my super secure password. And let's just check that the password is correct. There will be two prompts because it's a system keychain, and for some reason there will always be two prompts. And
awesome.
All right, that's basically it. And well, thanks everyone. And you will soon find the exploit on my GitHub. And I think within the next few days I will make the repository public. And thanks everyone.
Are there any questions? How much time did you invest to go through all of that work?
Actually, it didn't take me that long because I already knew about microbot replacement attacks, so most of the steps were very easy for me. And to be honest, finding this vulnerability wasn't too hard because I've sometime read about this guest code hosting article, and I noticed that it doesn't work, but I didn't look into that, and yeah, now I just thought, okay, let's look into that, and yeah.
So a week or weeks or
Maybe 2 weeks.
okay, that's a decent amount of work. Thank you.
This is kind of tangential, and you may have no idea, but I'm just kind of curious. Do you have any idea how the system key is generated, the per device key?
I just know that it's an AES key, and it's just generated at random. I think the first time you boot your new Mac, you reinstall it, then it will automatically generate as key.
Interesting. Thank you.
So when you brute force the task, why is that not like a vulnerability in and of itself?
Well, I'm not really forcing the taskbot. I'm just abusing the fact that the kernel has a list of recently used ports, and basically, whenever you send a process a new port that it doesn't know about, then the kernel will go through this list, just take one of the entries, and there's also a small generation number in there. And based on this generation number and yeah, the entry itself, it will generate your number. And basically, if you get the same generation number for an entry, then you will also get the same port number again.